Hello, my name is Kent Lidström and I'm the CTO of Smartoptics. I will be the one giving you this presentation with an introduction of 400ZR and what it means for you. During this presentation, I will give you a quick introduction to Smartoptics and this topic, and then I will go through some of the 400 coherent standards and then some of the measurement results with optical performance that we've seen. And last but not least, a case study with some of the learnings and experiences that we have from one of the real-life deployments that we have around 400 gig. If we look at an overview of Smartoptics, Smartoptics is a Scandinavian company that was founded in 2006. When we started, we were primarily focused on the optical devices and selling transceivers. And we have a strong history of selling fiber channel transceivers, and we are today certified with optics, fiber channel optics for both Breakout and for the Cisco MDS platform. Today we are also focusing a lot on optical solutions with main focus on open line system for different type of applications. We have our headquarters and our operations for the devices in Oslo, Norway. And in Stockholm, in Sweden, we have our R&D facility and the entire management team, and there we focus a lot on the system side. That's also where I'm located. We have some sales representatives in Europe and also in the US, but the majority of our sales are done through reseller and distributors that we have, spread across the globe. If we look at this topic, the 400ZR in disaggregated macro networks, what I'm going to go through here is some of our philosophy and ideas behind this. The traditional building concept of having a 400 gig client optics in your router going into a transponder that converted into a DWM signal that goes over a line system, is this a relevant building concept and approach for 400 gig? Well, it is, depending on what kind of standard you're choosing. However, when I look at this, and when we look at the 400ZR based on the OEF standard, they had a slightly different building concept in mind when they started to develop the products and when the standard was formed, and that was to run DWM optics directly embedded into the router. So you have the colored optics with the 400ZR coherent optics directly into your router port, switch port, run it over an open line system. And this is the type of building concept that I will focus on here today. And why do I think that this is a good way of running 400ZR? Well, it does provide a few benefits. It provides a lower overall cost because you get rid of a layer of optical equipment by removing the transponders, removing the client optics and so on. That also gives you lower power consumption, smaller footprint, and you will also get an overall lower latency because we don't have to go to the transponder. So once again, that's the concept that I will talk about here today. And then if we look at the standards and technologies around the coherent 400 gig, we have, I would say, 3 different initiatives today that are, heavily talked about. The first initiative, the 400ZR, is based on the OEF standard and specification. It was designed to be used for the data center interconnect with reaches up to 120 kilometers. It's limited in what you can do with a client and lines. It's a 400 gig client that goes out on a 400 gig line. That's all that is specified by OEF. And it uses a CFEC as a forward error correction on the line side and has a line modulation of 16 QAM. This is a relevant technology, very relevant technology for data center interconnect, where you plug the optics directly into a 400 gig switch router port. If you want to have a little bit better transport capability and want to be able to go longer distances and use it in a more transport-like condition, you're very likely to want to be able to use the OpenZR Plus standard. This is actually not a standard yet, it's just a multi-source agreement, but this is an evolution of the OEF-based 400ZR, where additional functionality has been added, so we can get a little bit longer distances out of it. So we can now go significantly longer than 120 kilometers. I'll come back to the reaches a little bit later in this presentation. Here we have a much higher flexibility on the client side. We can use 100 gig and we can use 200 gig and 400 gig Ethernet, and we can also have different line capacities from 100 gig, 200 gig, 300 gig, and 400 gig. That means you can use this with a lower line rate to get better optical performance. Then you use a different modulation format. So for the 100 gig and 200 gig, you would use QPSK. 300 gig, you will use 8 QAM, and for 400 gig, 16 QAM. That means you can actually use this together with a max bonder as well, where you, for example, take 4 times 100 gig into one 400 gig, and you transport that based on the specification that you have for that. But if you want to go further in network, you can actually go down on the line rate to 300 gig and only get 3 times 100 gig over that coherent module, and then you get a much longer distance. All of those line rates and formats are based on the OFEC for error correction algorithm. And last but not least, we have the open ROADM. I will not go through this in details, and I will very soon explain why. But those 3 initiatives, they have, I say, 3 different form factors that are valid for it. It's the QSFP-DD, OSFP, and the CFP2. All of those are designed to be able to be used for mid-span meet. So that means you should be able to take a module from vendor A and plug it in and run it toward another vendor. You should also be able to use an OIF-based DD directly connected to an OIF-based CFP2. So they should have a very standardized optical side, but also on the common management. I will come back to that on the next page. And we will focus today here on the OIF 400ZR, OpenZR Plus, and also this form factor. Why? Because this is what we see as the most common combination for this embedded approach. OSFP would also be a very good form factor for this. However, it's primarily Arista that have focused on the OSFP, even though OSFP is actually better technology than DD. The industry, the rest of the guys, they've selected to go with DD. So this is by far the most common interface, and Arista support this as well. On the CFP2 side, that is very associated with the open ROADM part, where you add also the OTN framing, and also you add typically a micro EDFA, so you get a higher power level or TX power level from this. This means that this combination is typically used together with transponders and max bonders. And since I was going to focus on the embedded approach, I will not discuss that kind of any further. So a module like this is actually very, very complicated. So it's like magic that they can get this to work. If someone would have told me 5-10 years ago that we would be able to have a 400 gig coherent module built into this form factor, I would say, no way, that's not possible. But here we are. So if we look on a high level, the functionality of this, we have a electrical interface on this side that faces the circuit that you have on your circuit board that uses a PAM4 modulation. So basically you have 8 lanes with 8 times 25 giga board, and that means that you have 8 times, since it's PAM4 modulated, you have 8 times 25 gigabit on the client side here, giving you your 400 gig. This is then going into your DSP, or the digital signal processor, that's doing some magic around this, and then you take it through your silicon optical subassembly transmitter block, where you add a coherent signals and so on. And then you go out on a standard LC connector, kind of a duplex connector here with one transmit LC and one receive LC connector. The line side will have a 16 QAM modulation. So it's amazing that all of this fits into this small form factor. The optical what the optical line should look like is well specified, as I mentioned on the previous page, but also the configuration of those is well specified through the Common Management Interface Specification, CMIS. This is now something that you have to keep in mind in order to be able to support in the 400ZR optics you have to have a switch and router that support the latest and greatest CMIS specification, because the coherent modules comes with an add-on in order to set wavelengths and so on. But if it supports it, it's supposed to be that it's completely, I say, agnostic for vendor. So all of the vendors should implement the functionality the same way. So the modules today, are they available? Well, the OIF-based ones that are available. We have shipped them in a quite large quantities actually in real deployments to customers. They support the OIF-based application modes. I will come back to that very shortly. And we do expect to see that we will get the OpenZR Plus based transceivers released during Q2 as well. There are still a little bit longer delay or lead times than for other optics, because those are still new and just coming out with kind of a limited availability when it comes to production capability at this point. But as a technology, the product themselves are GA. I mentioned this application mode, so I will spend a minute or two around this. So the OEF base supports 2 application modes. Our OpenZR Plus transceiver support 11 different application modes. So how is this supposed to work? Well, the switch reads from the optics what kind of capability do you have. The optics present that in a standardized way. I support those either 11 application mode for the OpenZR Plus or the 2 application mode for the OEF-based 400ZR. Then the user that configure the switch sees, okay, those application modes are available, then I want to run this particular application mode. For example, application mode 1 or application mode 6 or whatever they want to use the optics for. And when they then set that, the optics will be configured in a slightly different way. What does that mean? Well, if we take the first application mode, if we run this in application mode 1, according to the OF specification, it should then support at least 80 km. That means you need a preamplifier and a booster amplifier. So you will have some optical noise added to it. Then your receiver sensitivity will be changed to minus 12 dBm input power level. When you have a lower power than minus 12, you will start to get an alarm. That is something that the module will automatically change for you when you set it in application mode 1. If you instead want to run this directly over a dark fiber, you set it in application mode 2. So this means non-amplified. Then you don't have any optical noise to deal with. Then the receiver is more tolerant and can handle a lower input power. So when you configure this in application mode 2, then your receiver sensitivity level and your thresholds will be changed automatically, and you will start to get an alarm at minus 20 dBm. That is now your new receiver sensitivity level. So this is how it's intended to work. Does it work this way today? Well, it's a little bit hard to say, because today, as you know, pretty much all vendors have released several different flavors of switches and routers with 400 gig ports, but very few have released with GA software support for open 400ZR plus optics or OEF-based 400ZR optics. We do expect that pretty much all the switching router vendors will roll out this support during 2021. At this point, when we have done the testing and trials, it's either actually with supported software for a very few platforms so far, or with beta software that they've received at an early stage to test and qualify it, or where we need to do some tricks to get it to work. Another question that I get quite frequently is related to whether those optics, can you actually buy optics from any supplier and plug it in and get it to work? So basically, will the switch support MSA compliant or third-party optics? That is the entire idea behind the 400ZR. If that's going to be the case, or if the switching router vendors will try to lock the optics and force the customers to buy optics from them, we don't know yet. From the few cases where we've seen support for OIF-based, they have supported third-party optics or MSA compliant optics. So I hope that's going to be the case, but it still remains to be seen. We have a fairly good experience and we've tested it with multiple different platforms. So if you have specific questions, just reach out to us and we can see if we have an experience from your specific switch and router platform. If we then look at the optical performance around 400 ZR, what I've done here is I've mixed the topics a little bit based on the questions that I get. Quite frequently I get questions about how the 400 ZR will work in passive networks. And if you look at the passive network today, if you design, let's say, a low channel count passive network with 8 channel DWM filters or 4 channel DWM filters, they are typically based on thin film filter technology. And then the bandwidth of those will be around 30 gigahertz clear bandwidth and a little bit below 60 gigahertz of 3 dB bandwidth. That means you will not be able to fit in a 400 gig signal that will require at least 63 gigahertz of bandwidth. So the conclusion there is that the majority of the low channel count filters on the market today will not support 400 ZR, or they will provide a significant penalty to the 400 gig signal. There are other technologies like AWD filters. Here, those will typically have a sufficient bandwidth. However, then you have a challenge with the optical losses to those. So if I take the worst case numbers for a standard 40 channel max, it can be up to 12 dB. Typical values will be lower, but worst case can be up to 12 dB. The optical budget for 400 ZR optics, it's 11 dB, based on minus 9 dBm transmit power and a receiver sensitivity of minus 20 dBm. That means you only have 11 dB to play with, and to run that over a filter that has a loss of 12 dB provides with a negative capability. So all in all, that's not a good solution either. So the question is there a way to run 400 ZR over passive networks? Well, absolutely. Just use new type of filters with higher bandwidth. If you go to your current provider of passive filters and ask them for a 400 ZR capable filter, it's very likely that they are either working on qualifying those or already have them in place. Because this is something that at least we see as a requirement from a lot of customers today. This is of course good for the greenfield deployments. However, it will be a challenge for all your deployments that you already have in the field today. It's very likely that they will not, based on standard and specification, fulfill the 400 ZR bandwidth requirement. So that could be good to know. If we then jump over to some of the optical performance over the active line system, this graph here is showing two things at the same time. We have the two different limits and the two axes here. On the bottom, you can see the fiber length. The length is actually not really relevant. It's actually the fiber loss that is more relevant, but I will come back to that. We correlate this now to fiber length. Then you have the prefect bear on the left side here, and that corresponds to the graph at the bottom. So when we run this up to 80 kilometer or almost up to 100 kilometer, we don't see any degradation on the prefect bear. But once we start to go beyond this, this is actually based on a standard amplifier with a noise figure of 5.5 dB, and it has an optimum gain on 22 dB. We will start to see that we get a slight penalty on an OSNR penalty when we go up in loss or distance. And once we get here close to the 140 kilometer mark, we cross the solid limit here where we have the limitation of prefect bear. We have to be south of this to be on the correct side of the specification. And if we then look at the top graph, it corresponds to the OSNR graph on this side. So at this point where we run it up to 100 kilometer, we see that we are above 30 dB in OSNR. So we have a great deal of margin. The limit here is the dotted line at 26 dB OSNR margin. and from around 100 kilometer we start to see slight degradation that quite quickly go down here at the bottom. So the conclusion here based on the measurement that we've done is that you will have almost no degradation on fiber length up to 100 kilometer, or more importantly 22 dB link loss. And we feel very safe to commit to transmission distances up to 120 kilometer, or once again, more importantly, 26 dB link loss. So that's what you should expect to see from an OIF-based 400ZR optics. If we look on how well those will performed over multi-links or kind of ROADM-based networks, here we've done a simulation on a network that looks like this. We've also been running the corresponding testing for it. This network now is based on the fact that we use ROADM with a preamplifier and booster amplifier in each stage. Each amplifier will be of a kind of a standard type, so not the high performance, no hybrid Raman. We use, standard alpha-based amplifiers with the same performance as I mentioned before. We run it at an optimized link configuration with 80 kilometer and 21 dB link loss. So this graph here that you see, or the table that you see here, is based on those conditions. If you would have one link that is much longer, that would significantly change this. So this is the ideal condition around the transmission. But when we simulate this, we will have a transmit OSNR before we even get to the first band. That's because of the booster amplifier. Then we will have an OSNR that goes down, or where the noise becomes more and more significant for each span that we passes. When we then look at the traffic formats, we have an OSNR tolerance corresponding to the different formats. If we start with the OEF-based 400ZR, we have an OSNR tolerance of 26 dB. That means we can run that on all links that has a higher OSNR in the simulation than 26. So this is the last one that has a higher OSNR of 26. So that means 3 spans could be used with the OEF-based optics. So if we start from here, we can jump 1, 2, 3. If we then take the 400ZR based on, or 400 gig based on the OpenZR Plus, that one actually has a better OSNR tolerance because it uses the OFEC instead. Then we have 24 to correlate to, where we have a number that's just about 24. That's at 5 spans. That means in this case now, we can run 1, 2, 3, 4, 5 spans. That means in a network like this, we could run 400ZR, or 400 with OpenZR Plus standard, any to any in a network like this. You can have all combination. Those numbers are then, of course, based on theoretical simulations and also based on practical measurements, but the network conditions that you have might look slightly differently. So it would have to be a case-by-case simulation. But theoretically, that's what it will look like, and you get a good idea on the performance. On the OpenZR Plus, I mentioned before, we can go down in line rate here. So if we go down to, 300 gig, we are up at 10 hops, so then we can start to go quite long distances. At 200 gig, then we are at, above 20 hops, and if we go down to 100 gig, we can go, pretty much across the globe, very, very long distances. Then we have the CD tolerance as well that we need to take into consideration. I would say for the 400 gig based on the, or for all those formats based on the OpenZR Plus, this is not going to be super relevant. However, for the OIF based, the specification only specify a chromatic dispersion tolerance of 240 picosecond, 2400 picosecond per nanometer. And if we would look at the OSNR tolerance, I said that corresponds to 3 hops. 3 hops here would be 1, 2, 3. That's 3 times 80 kilometer. So that's 240 kilometer. Each kilometer has a residual dispersion on about 16, 17 picosecond per nanometer. So that would give us a much higher number than the 2400. So in that case, the OEF 400ZR will actually not be OSNR limited in a network like this. It would be chromatic dispersion tolerance limited. So that's something that you have to keep in mind, but that's a specific, unique situation for the OEF-based 400ZR. The other ones have such a high number here, so it shouldn't give you any penalty or limitation. So that was the optical performance slide. So my last slide here section is around a case study for a deployment that we've done with a European operator. So in this case now, the network that this operator has is, built on a number of dedicated rings. I think they at this point have deployed 5 rings. Each ring consists of 6 to 8 nodes. So it's both rings and there are also a bit of an interconnection in between. They decided to go with 400 gig in order to win this deal. So this deal, or their deployment here, is for a specific governmental win that they have to build a government network that they will build with 400 technology. So they had to go with this technology to win that deal. They have an interesting combination of transporting those 400 gig because they combine pretty much all the different technologies. So they run on some of the links, they run the 400ZR optics between 2 sides directly on a dark fiber. So they have certain segments on the network where they are very fiber rich. So then they take one dedicated dark fiber for that 400 gig service. They have some other links where they have passive networks where they only want to put a couple of 400 gigs, so they use a 4-channel passive filter for that. And they have other links where they don't have a lot of fiber and where they already have an open line system in place. So there they combined it with running the 400ZR over an active open line system. So this has of course been a great opportunity for us to test the different applications in different real life scenarios. And it's been going very, very well and very smooth the entire deployment scenario here. The benefit that they saw around this was it would reduce the number of gear, the network equipment, to provide lower power consumption and smaller footprint in the network. Also, in this case now, they run it like some of the router guys promote with a router-to-router hops, so they don't have any kind of roading capability in this network, so everything is point-to-point traffic, so it just jumping to the next neighbor. But all the protection will be done on a higher layer, layer 2 or layer 3 packet layer, and none of it will be done on the optical layer. And this was the solution when they did their math that provided the lowest cost per bit and made them successfully win this governmental deal. So that was one of the examples of the real deployment that we've done. So it is actually happening right now, and it's very exciting. This has been a big topic on all the optical conferences for the last 3 years, but now it's finally happening. So that's very, very exciting. So last slide here, question and answers. I think we will have a session around that a little bit later here when we will go through this. And so I want to take the opportunity to thank you for listening in. And if you have any additional questions later on, don't hesitate to reach out to me or to Peter, that is covering your region as a sales representative. Thanks a lot, and bye-bye.